start. Matteo? Should we? Okay. Should we start now or wait for?
Maybe you start.
Okay, let's start. People will arrive. Okay, so let's quickly recap what we did yesterday. So I told you that the main subject of this course is how to infer a probability distribution from data, and in particular with a focus on biological data. And well, biological data are typically few data, so we will mostly be working in a regime where we don't have many data, and and we want to infer some probability distribution over this data and possibly make a model of what's going on. So yesterday, to start, we introduced the notion of entropy. We saw that entropy quantifies the information contained in a probability distribution that you think as probability of a set of messages, and you can interpret entropy as the average information contained in these messages, which is precisely defined as the minimal number of bits that you need to encode the messages, okay? We have applied this to a few examples, and we have seen that we can compress the messages, but when we apply this to biological data, we have seen that there are correlations, there should be correlations, but we don't see the correlations just by trying to compress them. So there must be more complex correlations that the compression programs cannot really detect. And then we saw the simplest, let's say, method of inference, which is maximum entropy. So you have some data. From the data, you collect some statistics on some quantities that you are interested in, for example, the average of something. And then you say, okay, my probability distribution will be the probability distribution that maximizes the entropy, so it maximizes the uncertainty, so it's the least biased distribution that is consistent with the statistics that I have, okay? And we have seen that you can use this also to design a probability distribution that achieves some goal. For example, if you want to cheat, and you want to cheat in the most undetectable way, you can try to maximize the entropy condition to the cheating you want to introduce, and this will give you the least biased distribution that makes what you want to do, okay? So, fine, so maximum entropy is useful. By the way, maybe is there any chalk somewhere? Ah, there. Thank you. So now we want to be a bit more general, and as I said yesterday, I would like to discuss Bayesian inference, which is more general than maximum entropy, and I will show you that maximum entropy is a special case of Bayesian inference, essentially. So we started introducing Bayesian inference. I think you are all familiar with it, so I will not repeat. And we can go directly to the problem we want to study. So the problem we want to study is that we have some data. And let's say that data are some vectors, y. These are vectors in dimension L. L is the length of the data. So typically, in my applications, these will be biological sequences, for example. So it will be, for example, a protein sequence of length L. So you have L numbers. Let's take them as real numbers. Then, I mean, in some applications, they can be discrete. But and you have M data. So there is an index mu that goes from 1 to M. And M is the number of data you have. So, okay, so you can encode the data in a matrix, Y. So Y is going to be the set of all the y mu, and this will be a matrix M times L. Okay, so each line of the matrix is one data point. Okay, you can imagine Y where this is L and this is M. Each line is one data vector, and then you have columns that are the entries of the data vector. Okay. Then what we want to do is to infer some probability distribution. How we do that? We use Bayesian inference. So we have to make a model. So in maximum entropy, we choose some observable that we want to constrain. In Bayesian inference, we have to make a model. As I was saying yesterday, you have to start with a prior that is already some model of the world you have in mind, and then you have to update your prior in light of the new data that you have, and you get the posterior, and you can keep going if you have new data. So we have to make a model for the likelihood. This will be our model of how data are obtained given some parameters. Okay, so theta is going to be a vector of parameters we want to infer, and this will be the probability distribution we want to learn, which is the probability distribution of the data given these parameters that we want to learn. So this will be our model of the data generation process, and we are going to assume that the data are independently and identically sampled from this distribution. Okay? Then we need a prior. So the prior is what we believe about theta before receiving any data. And from that, we can get the posterior. So the posterior, according to Bayes' rule, is going to be the probability. So if we have M data, the probability of the M data, so sorry, here it's all the data. So the probability of theta given all the data we have is going to be the product over mu of the probability of y mu given theta times the prior divided by the normalization, where the normalization is nothing but the integral over theta of the numerator. Okay. We can also rewrite this in a more useful way, which is an exponential of m times 1 over m times the sum over mu of the logarithm of p of y mu given theta. Okay, I just take this product and I write it as the exponential of a sum. And then, well, then there will be plus the logarithm of p of theta, the prior, and then it's normalized by p of y. I will explain why I prefer to write it in this way later. Okay, now given the posterior, we can, if we want to decide, if we want to infer theta, we can do several different things. We can define several estimators for theta. For example, we can maximize the posterior. So this is called maximum a posteriori estimator. So we can say theta star is going to be the argmax of p of theta given the data. Okay, so you maximize, you take the most likely value, or you can take the average. So you can take the average of theta over the posterior. This is going to be the integral of theta times p of theta given y. Or you can just sample one value of theta from the posterior, okay, and decide that this is your estimate for theta. You can do other things. I mean, you can do what you want, but these are possible ways to get one set of parameters from the posterior. Okay, so this is the idea. Now, I just wanted to stress, maybe maybe this is already familiar to you, but I wanted to stress once again that what I like about Bayesian inference is this iterative nature. So you start with a prior, which is your model of the world when you don't have data. You receive data, you update your prior, and then you receive more data, and you... So just to illustrate this, let's say what happens if you have one data point. I just want to make this more explicit. If you have one data point, your posterior is this. Right? So you start with a prior, you receive one data point, you update, and this is your posterior, which will be your next prior. So this is your model of the world after you got one data point. Now if you receive one more data point, the probability of theta given y1, y2 is going to be the probability of y2 given theta. So if you assume that y1 and y2 are independent, then this object is going to be the probability of y2 times the probability of y1 times p of theta divided by p of y1, y2, right? But what is, I mean, can we rewrite this in terms of the prior after one data? Yes, because we substitute this here, and this is nothing but p of y2 given theta times p of theta given y1 times p of y1 divided by p of y1 and y2. And what is this? This is p of y2 given theta times p of theta given y1 divided, now p of y1, y2 divided by p of y1 is p of y2 conditional to y1, right? So you see that this is the next iteration. So you, at the beginning, you have no information. You start with a prior. You get some information. You update your prior. And now at the next step, this is your prior. You get new information, that is y2. And you, again, update your prior. And you update it in the same way. So you multiply the likelihood of the new data by the prior. The prior after y1, and you normalize, and what you have in the normalization is the probability of having y2 condition to y1. Right? And then you can keep going. And so the more you get data, the more you can update your prior belief, your model of the world. Okay? So what I like of this idea is that you can be... Sorry? Yes? No, these are just sampling of some distribution.
Okay, but then you should know the probability of because you plot you need p of x1 by 2.
No, because this is just the integral of the numerator. So what I need is, I need p of theta.
Yes.
This is my model of the world. And I need p of y given theta. This is my model of how data are generated given theta. And then the denominator is just the integral of the numerator. So I mean, what I like of this process is that it's very, you are very open to new information. The more you get information and the more you are willing to update your view of the world, which I think is a positive way to proceed. Okay, anyway, this is more like interpretation. Okay, now let's try to apply this to a concrete problem. And what I want to discuss, maybe you have already seen it, but I think it's a nice example, is what is, thank you, is what is called the Laplace problem. And I think the Laplace problem is probably among the first applications of inference to a biological problem. So I think it's right on the subject. So the Laplace problem was the following problem, is the following problem. So Laplace had some data, and the data were he had access to the records of the kids that were born in Paris. So we are in Paris in 1745 we are in Paris in the late 17th century, and Laplace had access to the record of all the kids that were born in Paris between 1745 and 1770. And he had access to this data, and the data were, okay, a kid is born, is it a boy or a girl? We take binary classification. So to each birth, you can assign a variable, y mu, these are your data. And let's say that 0 is a boy and 1 is a girl. Okay? So in particular, Laplace had access to a lot of data. M was 493, 472, so about 500,000 births in Paris in that period. And out of them, you can construct the sum. You can count. So I call y the sum over mu of y mu. So I count 1 every time there is a girl. So this is the number of girls, which was in the data 241,945. Okay. And the number of boys is m minus y, which is whatever, 251, 527. So the question, these are the data. The question of Laplace was, well, they are roughly half, but there are a bit more boys than girls. So is it a fluctuation, or is there something in the biology or somewhere that makes a bit more likely for a boy to be born than a girl? Okay? So this is the question. So what we want to estimate, so our model for the data is that each birth is an independent event, right? I mean, this is not this is an assumption, of course, because there might be correlations. For example, I mean, you can have twins, you can have something, I mean, correlations within a family. I mean, you can imagine all sorts of correlations, but we are going to assume that each birth is an independent event, and that the probability of y equal to 1 given theta is, let me just use I want to call, yeah, it's just theta. So I call theta the probability that a girl is born, and 1 minus theta will be the probability that a boy is born. So, Of course, theta will be a number between 0 and 1. And let's say that at the beginning, before we have seen any data, we can be the most unbiased, and we can say that our prior information is that P of theta is equal to 1. So we take uniform probability between 0 and 1. Any value of theta is equally likely. Okay. So what is the posterior? Well, the posterior is what we want is the probability of theta given y and m. M is not, I mean, m is a parameter, it's not like, is not data, but okay, it's the number of data. So what is the probability of y? Y is the sum of many Bernoulli variables, so it's a binomial. So the probability that if you throw a coin many times, that you have a certain number of heads, is just a binomial. So this is going to be m choose y times theta to the y times 1 minus theta to the m minus y, right?
Here you say the probability to have a girl knowing theta is equal to theta. This theta is the same thing, like the first theta.
Yeah, it's the same. So I'm just saying I want to estimate, the parameter I want to learn is the probability that when a kid is born, it is, the kid is a girl. Okay, this is my parameter.
Isn't this the probability of y given theta? The one you brought up there.
Yes, sorry, thank you. This is the probability of y given theta, but actually, no, actually, yeah, it is that. Sorry, yeah, thanks. Yeah, it's about the normalization. This is, yes, so this is for one data point. So let's, okay, sorry, this is y mu, okay? So for one data point, the probability that that particular kid is a girl is theta. This is what I want to learn. And then when I have many data, the probability that the sum, that the total number of girls is y out of m births is given by this. Thank you. So the posterior, okay, now the posterior is what? It is this times the prior, but the prior is just 1. I'm assuming uniform prior. So it's going to be this divided by the normalization. So the normalization is the integral over theta of the numerator. So in the numerator, I have the likelihood, and then I have to divide by the integral over theta of the likelihood. This term is independent of theta, so I can drop it. And what I get is theta to the y times 1 minus theta to the m minus y that I have to normalize over theta. So here I will have the integral between 0 and 1 in the theta of this same quantity, okay? So this is my posterior, okay? Now, you can compute, okay, is it clear? Sorry for the confusion. Now, you can compute the integral in the denominator. So the integral in the denominator is just a product of gamma functions. So this term here is just equal to gamma of y plus 1 times gamma of m minus y plus 1 divided by gamma of m plus 2. Okay, so this is the denominator. It's not very important. But in particular, what you can compute are the estimators that I defined before. So the maximum value over theta, you have to maximize the numerator. It's very easy. Is obtained for theta equal to y over m. This is what you expect. So you take the fraction of girls from the data, and this is the maximum a posteriori estimator. The average value of theta is equal to y plus 1 divided by m plus 2. And you can also compute the variance of theta from this. And the variance is given by y plus 1 times m minus y plus 1 divided by m plus 2 square, m plus 3. Okay, not very important. What is important is that, you see, when you have many data, so if m goes to infinity, so if m is very large, and y is of the order of m, which is the case here, y is about half. We know that more or less half of the birds are boys and the other half are girls. This will go to this is some number. This is very close to this because the plus 1 and the plus 2 are irrelevant. And the variance goes, well, this is proportional to m, this is proportional to m, and here you have an m cube. So the variance, as you expect, is proportional to 1 over m. So if you are in this regime where you have many data, whatever estimator you choose, you get more or less the same result. Okay. Now, one observation, however, is that if you have, for example, if you have, suppose that you observe m birds and there is no girl, okay, they are all boys, then the probability, what would be the probability of theta given that y is equal to 0 and m? Well, I just erased it, but if you take you get, if you specialize what I just erased to theta, to y equal to 0, you get an exponential. No, because there is, y is, I'm assuming here that y, this is when y is proportional to m. So if you believe that half of the kids are boys and half are girls, then y will be m over 2, for example. So y will be proportional to m. So when y is proportional to m, this is m, this is m, this is m squared, and this is m. So overall you get 1 over m. But if y is not proportional to m, so for example if y is equal to 0, then your posterior is going to be this. And in this case, so this is sorry, it's not an expansion, it's a power. So you get something like p of theta is something like this. Okay, so it's decaying. So in this case, the most likely value, that is theta star, is equal to 0, but the average of theta is 1 over m plus 2. And in that case, I think, I mean, again, this is, you have to interpret the result, but it's more reasonable to say that you choose the average as the estimator instead of the most likely value, because the fact that you observed 0 girls is not really telling you that the probability that a girl is born is 0. It's telling you that the probability is of the order of 1 over m or smaller. But you know, if you have m data and the probability is of the order of 1 over m, it means maybe the next birth can be a girl. Okay, so these estimators, you have to interpret a little bit the posterior and choose the correct estimator. This is just a little remark. Okay, anyways, now back to the Laplace problem. So if you take this data, then I will erase them, and you put them here, what you get is that theta star is 0.490291, so it's very close to 0.5, and the variance the standard deviation, better. The standard deviation is 0.000712, and the average is basically equal to theta star up to this digit. Okay. So from this you can conclude that what can you conclude? I mean, is it possible, is it compatible with the fact that theta is equal to 0.5 or not? Well, you see that theta star minus 0.5 is actually much bigger than, because theta star minus 0.5 is of the order of 0.01, which is much bigger. It's 2 orders, well, no, not 2 orders, well, 1 order and something bigger than the standard deviation. So you are at more than 10 standard deviations away from 0.5. So from this you can conclude that 0.5 seems unlikely. So there must be something in the process that is biasing a little bit the births, and it's making the birth of a boy is a little bit more likely than the birth of a girl, which is something that now is very well known, that boys are a little bit more at birth than they die sooner. So overall in population there are more women, but okay. Fine. Okay, so can we be a little bit more precise on this? Can we really estimate the probability? So we would like to estimate the probability that theta is 0.5. So now theta star is smaller than 0.5. So what we can ask is, what is the probability that theta is bigger or equal than 0.5 given the data we have? Okay. So this quantity is the integral between 0.5 and 1 of the posterior. And how can we compute it? So, well, of course numerically, but Laplace didn't have computers, so you can do some estimate of this by the Laplace method. So how do you do that? First of all, we remember that the posterior, so we can rewrite the posterior that depends on y and m as a function of theta star and m, where theta star is just y over m. So we write that y is theta star times m, and then we get theta to the power y, which is m theta star, times 1 minus theta to the power m minus y, which is m times 1 minus theta star. Okay? So this is the numerator of the posterior, and then it has to be normalized. So we can call this object the exponential of minus m times a function of theta that depends on theta star. Okay? So if you write it explicitly, the function of theta, maybe I can write it here. This function f of theta star, f of theta that depends on theta star is going to be minus theta star log theta minus 1 minus this times okay. So the interesting point is that the posterior is exponential in m times a function of theta. And so these integrals, when m is large, can be estimated by the Laplace method or saddle point method that was invented by Laplace for this kind of problems. So first of all, we have to normalize the posterior, so we have to compute the normalization. Okay, first of all, we have to plot the function f. So the function f, what is the shape of the function f? You can plot it. It's defined between 0 and 1. It will diverge when theta goes to 0 and when theta goes to 1. So you get something like this. Well, it's not 0 here, but. So it has a minimum when theta is equal to theta star. And then it diverges when theta reaches 0 or 1. So because the posterior is the exponential of minus m times this function, this is f. The posterior, which is exponential of minus m times this with m very large, the posterior is going to be extremely peaked around theta star, right? And this is why we have found that the maximum likelihood, the maximum a posteriori, and the average basically coincide, and the variance is very small because this is a large deviation probability where that is exponential in a large parameter. So it's becoming extremely narrow when we have many data. Okay, so now how do we estimate this integral? First of all, we have to normalize. So in order to normalize, we have to compute the integral of this. And the integral of this kind of object can be approximated by expanding f around the minimum, right? The minimum is the peak of the integral. So you do an expansion around the minimum. And what we get is the function computed in the minimum. And when you expand, the first derivative is 0 because it's a minimum. So you have to put the second derivative. When you put the second derivative, you get the Gaussian integral. So you can do the Gaussian integral, and you get square root of 2 pi divided by m times the second derivative. So this is the saddle point method. You approximate this kind of integral by the minimum of the function with a correction that comes from the second order fluctuations. So first of all, we can write the normalized posterior up to very small corrections. So our normalized posterior will be exponential of minus m times f of theta minus f of theta star. Because this factor goes in the numerator, and then you divide by the square root of 2 pi over mf second. So this is the normalized posterior up to small corrections in 1 over m. And then from this, you can now estimate the probability of theta being bigger than 0.5. How do you do that? So theta star is smaller than 0.5. So 0.5 is somewhere here. So you have to compute the integral of this part, which is very small. And here the derivative of f is not 0. So what you will do is to expand around 0.5. Okay, so you take this integral and you expand p of theta around 0.5. So you write this as, when you develop, you will have exponential of minus f of theta star in 0.5 minus f theta star of theta star. This is when you compute this object in 0.5. you have the normalization. So you have square root of 2 pi divided by m f second of theta star. And then you have a small correction that comes when you take the first derivative here, and you get an exponential integral. I don't do all the calculations because they are easy. You can do them by yourself. So this will just give you an additional factor here of f prime of 0.5. OK? And so this is the final result that Laplace got. All these quantities now can be computed with paper and pen. And what you get is that this object is of the order of 10 to the minus 42 with the data that Laplace had. So the conclusion of Laplace was, OK, the probability a posteriori that theta is 0.5 or bigger is 10 to the minus 42, which means I can safely conclude that it is more likely to give birth to a boy than to a girl. This is what the data tell you, OK? And then you can try to understand why, and this is complex biology, but at least the data are telling you something very precise, OK? So you see that this is what is called asymptotic inference. This is a very favorable regime where you have many data and few parameters. Here you have one parameter and 500,000 data. So you can safely make statements like, OK, the probability of my result is 0. And why it is so? Because the posterior, when you have many data, the posterior becomes exponential in m. So you get a large deviation structure. And so the probability of a deviation of theta from the maximum a posteriori result, which is theta star, is exponentially small in m. So it decays very fast. The more you have data and the more the probability of saying that theta is different from the theta star is small. But you can quantify also small, because you see that the probability, now I did it for 0.5, but you can generalize this calculation for any a. If you put a here, so the probability that theta is bigger than a, and a is bigger than theta star, is just this, right? So you can say that not only for any a bigger than theta star, this quantity is positive, and the probability goes to 0 exponentially, but you can say how fast it goes. So you can say that in order to exclude, if you want to exclude the value of a bigger than theta star, what you need is a number of data that is much bigger than this prefactor. So given this large deviation function f, in order to rule out a deviation from theta star, which is the minimum of f, you need an amount of data that you can quantify. You know how many data you need. If you want to exclude a equal, I don't know, now we excluded 0.5, maybe you want to exclude 0.492, and then this estimate tells you how many data you need to do this. OK? Any questions up to this point? Yes?
We assume that uniform time, but by looking at the numbers, we know that the theta should peak around 0.5. So
yes.
like a Gaussian prior, how does that change?
Exactly. So this is the next step, but I can answer immediately. So suppose I add the prior. Well, maybe let me answer this in general. So let's do it in general, and then you can think about what happens in this case. So yeah, what's the role of the prior? I was telling you at the beginning that the nice thing of Bayesian inference is that you update your belief the more you have data, and the point is, does the initial prior you have play a role or not? And my statement is that in the asymptotic inference regime where you have many data, the prior becomes irrelevant. So whatever, I mean, with some, okay, let's discuss this. And so now let's redo all the calculation very quickly in the general case. Okay. So in the general case, I choose a prior. I choose a model from the for the data. I write my posterior. The posterior is, I wrote it as exponential of m times 1 over m times the sum of the log likelihood plus the log of the prior, and then normalized by the integral over theta of the numerator. This is my posterior. Now, let's assume, let's make one more assumption. Let's assume that the data, y mu, are generated according to the same model. So let's assume that my model of the world is correct, except that I don't know the value of theta, okay? So the data are going to be generated by the probability of y given a certain theta hat. And theta hat is the true value, okay? This is the true biological value of the probability that a girl is born, that I don't know, but I know the model. So for the Laplace problem, the model was Bernoulli, and Bernoulli is correct. The problem is I don't know theta hat. So what I have to do, so this I don't know it. I make my choice. I know the data. So I don't know this, but I know the data. And I want to infer theta hat from my Bayesian calculation. So now look at this term here. This term is 1 over m sum over mu of the log of p of y mu given theta. So this quantity is a random variable because y mu is a random variable. So this is a sum, is the average over m, over the data, and of some random variable. Now by the law of large numbers, essentially, when m is large, this will converge to the statistical average of this random variable. Okay, this is a random variable, depends on y is a random variable. So this will converge to the expectation of this over the process that generates the data. So this is going to be the integral over theta. The data are generated by this probability. So this will be the integral over theta of the probability of y given theta hat, which is the true value that I don't know, times the log of p of y given theta. Okay? Can I write this in a better way? Yes. I can write this as integral over y of p of y given theta hat times log of p of y given theta hat minus integral over theta of p of y given, sorry, not theta, y. Sorry, this is y. Integral over y, because the random variable here is y, okay? Theta hat times the log of p of y given theta hat divided by p of y given theta. Okay, I just took this, I sum and subtract this. So this term and this term cancel, and this is this. But now we recognize things that we have already seen yesterday, because this object here is the entropy. This is minus the entropy associated to the distribution P with theta hat. And what is this? This is the Kullback-Leibler divergence. So this is minus the Kullback-Leibler divergence of the distribution with theta hat and the distribution with theta. Okay? So when I have many data, this object converges to this function of theta and of theta hat. Theta hat is unknown and is fixed, okay? Is the true value I want to infer. So I can rewrite the posterior. The posterior is going to be exponential of minus m. Now note that, okay, I will have exponential of minus m times the entropy of theta, but theta hat. But theta hat is a constant, is an unknown constant, but what I want is the dependence on theta. So this term is a constant that I can drop because I'm going to normalize in the denominator, so let's not put this. So I will get exponential of m times the Kullback-Leibler divergence of theta hat with theta, which is this term, plus the logarithm of the prior. Okay, and then I have to divide, I have to normalize this by the integral over theta of the numerator. Okay? Now, remember that we said that the Kullback-Leibler divergence is always positive. It is always positive and is equal to 0 only if the two distributions are the same. If and only if. So, can I, sorry, maybe I'm erasing too fast. Tell me if I should not erase something. So now I recognize again a large deviation structure where I have the exponential of m times a function. And this function, I mean, now this is true, not, I mean, now theta can be also a vector. I say theta could be a vector of parameters of dimension d. What is important is that the dimension should be fixed. So now I'm looking at large M with a fixed number of parameters. But schematically, this quantity, dkl, is going to be something that has a minimum, in 0. And otherwise, it's always positive, and this is theta hat. So what is the shape of the posterior then? This is the posterior, p of theta hat, given the data. Again, I have exponential of minus something very large times something positive that is going to be very strongly peaked in theta hat. So when m is large, this is going to be very peaked. And this is the contribution from the likelihood. Now, to answer your question, the prior, what is the role of the prior? The prior, you see, the prior is not multiplied by m. So if m is 500,000, this term is super large. This term is order 1. So this is a subdominant contribution that is going to modulate a little bit. So if this is the likelihood part, the prior is just whatever I choose, a Gaussian or uniform. This is basically becoming a delta function in theta hat. So whatever prior I choose, unless I exclude theta hat, so if I have such a strong belief that I give 0 probability in the prior to theta hat, okay, and then in that case, okay, I am in trouble. So as long as your prior is non-zero everywhere, so if you are not, bold enough that you say, okay, 0.5 or whatever, the correct value, I exclude it from my space of possibilities. This term is basically, when this term becomes a delta function, this will give you logarithm of p of theta hat that is a constant and will drop out of the thing, okay? So this shows that the prior in the regime, in the favorable regime of asymptotic inference, where you have many data and few parameters, whatever prior you choose, you will converge to the right result. And so this thing will go, essentially, this term will be a constant, so it drops with the normalization. This object is 0 at the maximum. So when you do the saddle point calculation in the denominator, you get 1 up to corrections. And so in the end, the posterior is just going to be exponential of minus m times the Kullback-Leibler divergence of theta hat with theta, up to non-exponential terms that are the saddle point corrections in the denominator. So this tells you in all generality that you always have the prior is irrelevant and the probability of making a mistake decays exponentially with the number of data you have. And not only it decays exponentially, you know how it decays. And the rate of decay is the Kullback-Leibler divergence. So if you want to rule out a certain value of theta, what you need is a number of data much bigger than 1 over dkl of theta hat and theta, okay? So the conclusion is that we are happy because we can do inference. If we have many data, we can do inference. Our prior belief fades away when we get more data, and we can be very quantitative in estimating how many data we need and how the process converges to the right value. Now, any questions? Okay. Now, to conclude this part, I just want to show that maximum entropy is a special case of this. And then I wanted to show you an application to some data. It will be fake data, but you can apply it also to real data. Yes.
Yeah. What if the data were not independent in the first place? What would
Yeah.
you have seen at the beginning, at the end of the?
Well, then you have to make a model of how correlated they are.
Now, let's say that at the beginning we didn't know that they were correlated. We suppose them
Independent, yeah.
So what would we have seen at the end of the calculation?
The answer is I don't know. It depends on how because the main step was to use the large the central limit theorem to say that 1 over m. So when I do Bayesian inference, I will always assume that they are independent. Now the question is, what if they are not independent?
How can I conclude at the end
Yeah.
of the calculation that they were not independent in the first place?
So, okay, let me say first the crucial step was to look at this quantity and say, okay, the central limit theorem tells me that this will converge to the expectation of the log of p of y over y. Okay? Now, if the y are correlated, it depends. We know that the central limit theorem for correlated variables can hold or not depending on the nature of the correlations, right? So this will not be true. If it is true, well, then this will be something that depends on theta and on the process that generates the data. But if my model is not correct, I was assuming that the model is correct. So that my model of the data, that the likelihood I am assuming is the right one. Otherwise, I get the Kullback-Leibler divergence between my model and the true one, which is something else. And it could be that the value of theta that I get is not the right one because my model is wrong, right? Now the question is, what if can I detect if the data are not correlated? Well, in that case, I think you can just look at the data and try to see if there are correlations between different data points. So you would have to look into the training set of your problem and try to detect correlations.
Yeah, but it
what is the question? The question is, how do I know if my data are correlated, or what do I do if the data are correlated?
The question was, can I understand that the data are correlated by computing these calculations?
No.
See a strange result of some kind?
No. This calculation would give you some value of theta, and it would, I mean, assume that the data are generated by a correlated process, okay, and assume that still the correlations are weak enough that the central limit theorem holds. You would still get that the posterior of theta, given the data, would be exponential of minus m times a function of theta, where the function of theta is this, is the expectation over the data of this. And this function will typically have a minimum, so you will get a result, okay? And the result is wrong, but you don't know it. We can discuss an example next week, for example, in proteins. When we do this kind of analysis in proteins, we have protein sequences, okay? And we put the protein sequences in a table where each line is a protein, okay? So our vectors y are going to be vectors of numbers, of L numbers, okay? And we can do this kind of process under the assumption that the proteins were generated independently by some probability distribution, and we get the result. So we can infer parameters, and the things converge, and we don't see any problem, assuming that they are IID. And they are not IID, because we know that proteins, natural proteins, have been generated by nature through evolution. So we know that there are phylogenetic correlations between the proteins. But this kind of procedure is not telling you that. In order to see that, you have to look at your data, you check, you realize that there are correlations between the data, and then you can try to improve your model taking into account this correlation. So this is an important point. In all these inference procedures, you are making a model of the world, so you are making a model of your data, and you are working under the assumption that your model is correct. And, well, the thing that can go wrong is that if there are such strong correlation that this thing is not converging, then you can get different results. But then you should have, you should have like strong power law tails in the distribution of this variable that makes that the average does not exist, and so on and so forth. Did I answer? Okay. Okay, so now I wanted to say that maximum entropy is a special case of this general scheme. And how do we see that? So in maximum entropy, what we do is we start from some data, then we choose some observables, let's say G, and then we compute the averages of these observables over the data, which means we compute the empirical average of G. Okay, let's say G can be several observables, but so maybe G is a vector of observables. And then what we say is that, okay, these will be some numbers, G bar. And when we do maximum entropy, we start from the data. We compute this expectation. Then we maximize the entropy under the constraint that the expectation of G should be equal to this number G bar that I get from the data. So we have seen that the probability that results from this has the form of the exponential of G times some parameters that I call theta now. Yesterday it was lambda, but it's the same story. And normalized, right? Now theta can be a vector if G is a vector. This is a scalar product. And then, in order to fix the theta, I have to impose that the expectation over the data of G has to be equal to the expectation over this model of G. This is the logical scheme of maximum entropy, right? What do I do when I do Bayesian inference? Or sorry, let me say it better. How can I put this in the framework of Bayesian inference? What I can say is that, okay, I do Bayesian inference. I want to say that this is a special case of Bayesian inference. So if I do Bayesian inference with a flat prior, so at the beginning or let's say uniform, constant prior, so then I have to normalize it properly, but uniform prior. So I say, okay, I have no prior belief. My prior belief is uniform. And if I choose a model, my likelihood is, okay, P of y given theta is this. So this will be my model of the world. So I say, okay, my model for the likelihood is an exponential with some linear combination of some observables that I choose. So I choose the same set of observables. Then, what is the posterior? The posterior is going to be the product. And of course, again, I assume that my data are independently generated from this likelihood. Then the posterior is going to be the product of the likelihood. The prior is uniform, so I don't put it. And, well, I have to normalize it. So the posterior is going to be proportional to the product of the likelihoods. And this product is the product of exponential of theta times g of y mu divided by z. So then I get exponential of theta times the sum over mu of g of y mu divided by z to the m, right? Where m is the number of data. And now if I want to estimate theta by maximizing the posterior, so my theta star, sorry, I write it here, let's say. Let's write it here. So theta star, the maximum a posteriori estimator, is going to be the argmax of the posterior. But I can also maximize the logarithm of the posterior. So it will be, let me maximize 1 over m times the logarithm of the posterior. So this will be the argmax. When I do 1 over m times the logarithm of the posterior, I get theta times 1 over m sum of g of y mu minus log z of theta, right? I take the log of this, I divide by m. And so this is exactly the argmax of theta times g bar. This is my empirical average, minus log z. So the values of the parameters theta are the values that maximize this quantity. And if you remember yesterday, we said, okay, in maximum entropy, you can obtain the parameters also by minimizing kappa. And kappa was the logarithm of z minus theta times g bar, which is minus this. So minimizing the free energy here, basically, well, minimizing whatever. Let's forget about free energy, there are the signs. Anyway, minimizing this thing is the same as maximizing the likelihood, okay, in Bayesian inference. So maximum entropy is a special case of Bayesian inference where you have uniform prior, a Boltzmann distribution for the likelihood, and then you do your inference.
On a finite domain of data, taking a constant prior for data is itself a maximum entropy distribution, right?
Yes.
So my question, if we have an infinite domain for data, we can take a uniform prior, but do we get the same result if we take the maximum entropy distribution as a prior for data?
So yes, because basically, again, here I'm implicitly, okay, this is true also for finite data, but if you have many data, then the prior is irrelevant. So when M is large, the prior will be irrelevant. If you have few data, then the prior becomes relevant, and then it depends on the prior you choose. So now, if you are on an unbounded domain, you can still take a uniform prior, which is not normalizable, but you can still say, okay, maybe I put a cutoff and I send the cutoff to infinity. And typically what happens is that the posterior remains normalizable, even if the prior is not normalizable, because the likelihood bounds the values of theta.
Okay, but this is not a consequence on the fact that you took the maximum entropy prior.
No, I would say it's okay. Now, to conclude, I just wanted to show you another application that is similar in spirit to the Laplace problem, but is maybe more relevant to contemporary biology, which is the problem of estimating the diffusion coefficient of some object from tracking data. So you can assume that you have some object diffusing in water, and you want to estimate, so you can measure the position of the object at several times by, for example, some tracking device, and you want to estimate the diffusion coefficient. Okay, so this is again is a tutorial that you find in the second book, the one that is the published one, and I also put it in the drive. So is this one diffusion coefficient? Now, okay, let me again open the book. Sorry. Okay. So in this book, it's the first tutorial, and the idea is this. So you have some object that you can track. So you can record the position, and you assume that this object is doing some Brownian motion. So we assume that okay, you have a Brownian motion, and you can measure at certain times ti. You can measure the position of the object in a plane. Okay, and let's assume that the problem is two-dimensional. Then, if you want, you can add the third dimension and see what happens. So you have a series of data that are three real numbers: the measurement time, the position xy, and the position y, the position xi and the position yi. And I goes from 1 to m. So you have m data points. And the goal is to estimate the diffusion coefficient of this object under the assumption that the object is performing a Brownian motion with isotropic diffusion coefficient and no drift. Okay? So in the folder, you have some data. These are fake data that we generated using Brownian motion. So it's not real biological data, but you can apply the same thing to real data. So, okay, if you take the data and you look at the files, and you look at the trajectory, you will see Brownian motion. So you see something like this. This is one trajectory. And if you plot the distance from the initial point as a function of time, you see something like this. So how do you estimate the diffusion coefficient? So the first thing you could do is to say, okay, maybe what I can do is just, and this is the first point, you can say, okay, let me give some rough estimate. So you can do, if you want to do a rough estimate, you could do two different things. So you know that in Brownian motion, the square of the displacement is proportional to time. So you can say, okay, let me look to the initial and final points. So this is the total displacement. And I can say, okay, I take I take r square, I divide by the time with the proper factor 4, because we are in 2 dimensions. And this will be my estimate of the diffusion coefficient. So I can say, okay, one estimate is d0 is given by the total displacement, total square displacement divided by 4t. And if you do that, this is the dashed line, okay? You would get a diffusion coefficient of 1.2 from this data. But the other thing you can do is to say, okay, in each time step, I can compute the increment. So I can compute delta xi, which is xi plus 1 minus xi. And then, of course, I can compute the same for and delta t. And then I can say, okay, I estimate the diffusion coefficient from each increment, and then I average over the increments. And this gives you another estimator for the diffusion coefficient. And if you apply this to the same data, you get something that is about twice the first estimate. You see that I don't know if you can see very well, but because, of course, you have finite number of data and you have noise, if you estimate in this way or in the other way, you get very different results. Okay? So which one is right? Which one is better? Well, to answer the question, we can try to do Bayesian inference and see what Bayesian inference tells us. So to do Bayesian inference, we should write the probability, the likelihood of the data. Okay? So here the times are not random variables. The times are fixed. It's the times where the person who does the experiment made the measurement. What is random is x and y. So we should write the probability of x and y given the model we have of the process, which is a Brownian motion with diffusion coefficient d, right? So we can do this, and we know that in Brownian motion, the probability of having an increment of delta x in a time delta t is just a Gaussian. It's this form. And we are assuming that the Brownian motion is isotropic, so it will be independent for delta x and for delta y. Right? So the final, the likelihood of the data, given the diffusion coefficient and the times, is going to be this product over all the increments. So you go from 1 to m minus 1, you compute these things, and you have, maybe I can write it here so that the probability of the data given d and the times is a product of Gaussians. So you get 1 over 4 pi d delta t I times the exponential of minus delta xi square plus delta yi square divided by 4d delta t. right? So now what we're interested in is the dependence on this object on D. So from the point of view of D, you have a factor D to the power minus m minus 1 in the denominator. And then you have exponential of minus 1 over D times a constant. And actually, and then you have a prefactor, but the prefactor will go away when you normalize the posterior. And actually, what you get here, this B, is related to the estimate of D we did before. So now, okay, we use Bayesian inference, so we write the posterior. The posterior is the, and okay, we use a uniform prior for convenience. So here, as you were pointing out before, this is, in principle, D can go from 0 to infinity. So in principle, you cannot use a uniform prior because it's not normalizable. But you can always say, okay, maybe, you know, let's say, okay, the diffusion cannot be more than something and not less than something else. So you put cutoffs, and then you send the cutoffs to infinity and to 0. And what happens is that the posterior will remain normalizable because the likelihood is constraining D enough. Now, what you see is that this constant B that appears here, so this factor here, is precisely the estimate of the diffusion that you would get by assuming that, by estimating it from the increments. So we can write this as D to the minus m minus 1 that comes from here. And here we have exponential of minus this object. I mean, the sum of these over I is going to be D star over D times m minus 1, which is the number of data that you have. So this is going to be proportional, the posterior, sorry, this is the posterior. Is going to be proportional to this thing. And so now, once again, you can normalize it. So you have to normalize it by the denominator. You can compute the denominator. It's again, it's a gamma function. So you get factorials. And you conclude that this thing is again an exponential in M. Okay, well, here it's m minus 1 because with the function f, and here it's particularly simple. The function f is minus log d, sorry, plus log d minus plus d star over d. Did I get the signs right? Yes, okay. So you can see that this function again has a minimum when d is equal to d star. So Bayesian inference tells us that let's say at least the maximum a posteriori estimator is, and so the correct estimator in Bayesian inference is the one is the second one. So the one that you get by taking the average over the increments. Okay? And as in the Laplace problem, you can compute, if you don't like the maximum a posteriori, you can compute the average of D. And you can see that when M is large, it will converge to D star. And the variance, again, is of the order of 1 over M. So if you have enough data, you will get a very peaked posterior. So you can do this on the data that we provide. So we provide in the folder, we provide trajectories, but you can generate your own trajectories if you want. We provide trajectories with 10 measurements, 100 measurements, and 1,000 measurements. You have to be careful when you want to compute the posterior, because in the posterior you have this factorial. So if you want to normalize it and you want to compute 1,000 factorial, is going to be a problem. So, well, you can approximate the factorial by the Stirling formula. And then this is the posterior. So you see, when you have 10 data, you get something like this. So it's very bad. It's very wrong, the maximum value, and it's very broad. And when you increase the number of data, your posterior starts to be strongly peaked. And you see that this star, when you increase the number of data, will converge to the correct value. I mean, here the data were generated by Brownian motion with diffusion constant 2.5. And you see that, well, you converge to the right result. So you can use this. And, you know, in biology, it is interesting because if you observe something, you would like to know what kind of object it is. And, well, different biological objects can have quite different diffusion coefficients because they have different sizes. And so you can try to infer what kind of object you are looking at by the way it diffuses. So, well, this can be useful. Anyways, this is an example of. Yes.
Because in the previous example where you are in the Laplace case, okay, or proteins, for example, okay, you have integers, okay, so there are no problems in your data. But here, for example, I can assume that on x and y, I have some measurement error because that confuse variable. Okay.
Mm-hmm.
And so, in principle, it's true that your result is well, it's obviously just given by the differences. Okay. But this assumes that your measure is exact.
Yes. Yes.
Whereas we know that when you do difference with those variables, I mean, your errors are increasing a lot. Okay?
Yes.
And so, I mean, how do you manage it?
So you can generalize the calculation, but it's a bit complicated. But I think it was maybe one of the questions. Maybe it was a. I don't know if in the end we removed it or not. I don't remember. Maybe not. Let's see. No, well, we removed it because it was too hard. But OK, you can imagine that here you have some measurement noise. And in that case, what happens is that the likelihood of the data will be this convoluted with the Gaussian. So you have to do a Gaussian integral, which you can do if your noise is Gaussian. And then, but the problem is that now, because you observe noisy data, now it's not just a product, they become, they are all mixed. And so then you have to invert a matrix. So, but you can still do it. And yeah, it's an interesting, if someone wants to try, it's an interesting exercise. So basically you have to write, again, the posterior is not going to be this simple object, but it's going to be this convoluted with the Gaussian and integrated over delta x and delta y. And then, sorry, integrated over the noise, not over, so you know the delta x, but so you have to integrate over the noise. So you get, but it's a Gaussian, so you know how to compute Gaussians, so you get a matrix. And then in order to get your estimate, you have to invert this matrix and do a bit of work.
So you're saying that we have to make with the same model, make the expectation with respect to the error if we are in the scenario.
In the noisy case, yes.
Yeah, and with that, it appears the convolution with the Gaussian.
Yes. So you get an additional convolution, and then you have to deconvolve, which means you have a matrix, and you will have to solve this. Okay? You can, if you're interested, you can think, and we can discuss. Okay, I can stop here for today, and then, so this is basically, so the message is, when you have few parameters and many data, you can be confident that you will get the right result. And now, from tomorrow, we will start to see what happens when you have many parameters and maybe not many data, and then things become more complicated.